down. Here we go. Let's share our screen. Here we go. Yeah, baby. Okay. So let's do this. Let's do that. Let's do that. Where's my chat? There it is. Very good. Excellent. Okay. Sorry. So 4.3 continued primes GCD. And we're going to see the today actually Euclidean algorithm. We shall also see an amazing theorem called Bezout's theorem, also known as Bezout's lemma. I learned it as Bezout's lemma.
How do you write the Bezout?
Bezout, let's write it properly. Bezout, French mathematician, known, I guess, only for that. I don't know. I that's the only result I know with that name. Bezout's theorem I will touch upon at the end of the lecture, but I probably won't have time to do much about it. I don't know. We'll see. What did we see yesterday? We saw, and I'm going to use that quite a bit today, we saw the fundamental theorem of arithmetic, which says that if you take any positive integer, n can be written as a product of primes in a unique way. And this is really important, okay? And today I'm going to use that, so you'll see maybe a little bit more what I mean by that. Next up is, I wanted to show you the proof that there are infinitely many primes, and then I'll move on to the GCD and all that. Sorry, let's close this. Okay. Yeah. Okay. Infinitely many primes. So let's do that. Theorem. There exist infinitely many primes. This goes back to Euclid, so that's a long time ago. The proof is really lovely. In fact, there are tons of proofs of this theorem. This is the original one. It's the simplest one. So here we go. So I'm going to show that there exist infinitely many primes. Now, the argument I could use here is just, I'm going to prove it by contradiction, but you can sort of tweak things around and not use a contradiction, but the argument is essentially the same. Okay, so so let's suppose for a contradiction that there are only finitely many primes. So suppose for a contradiction that there are only finitely many prime numbers. Okay, so if there are finitely many primes, I can make a list. So P1, P2, P3, and we eventually reach the last prime. So these are all the prime numbers that exist. That's our hypothesis. And we're going to try to get a contradiction out of this. Okay. And here's the trick. So the trick is to consider a number, let's call it big Q, which is you take all these prime numbers, you multiply them together, and you add 1. Okay, so I'm going to multiply all these numbers together, and I'm going to add 1. Okay. Okay. Now, this number, I hope you believe and see that this is bigger than any of the numbers P1 to Pn. It has to be bigger, right? You're multiplying all these numbers together and you're adding 1. So hopefully it is clear that Q is bigger than every Pi, right? Everybody is with me on that?
So the negative numbers aren't primes?
Sorry?
So the primes are only the positive numbers.
Yeah, I'm looking at it. I'm looking at everything is positive here. Yeah. Like that. Okay. So I'm multiplying out the Pi together, add 1. This number is bigger than all the primes, and hence it's not prime, right? So Q is not prime. It's not in the list. It's composite. So that means it must be divisible by some prime, right? Right? And the primes are P1, P2, right up to Pn. So let's say Pj. Right? So I've got all my primes, P1 to Pn. I've got the number Q, which is product of all the PIs together plus 1. This is bigger than all the primes, so it's not prime. So it's divisible by some prime. And since this is the full list of primes, it means that one of these numbers must divide Q. If at this point you see why this is impossible, this is fantastic. If not, let me try to convince you. That's why we have that plus 1 there. But this is impossible. Right? Because if this number Pj divides Q, right? And since it clearly divides the product of all these numbers, right? It appears in the factorization of this number. If it divides Q and it divides this product, it must divide their difference. Right? This is a trick we're going to use often. If you divide two numbers, you divide any integer combination of the two. And what is that? That's 1. But a prime number cannot divide 1, right? So this is a contradiction. So that's the proof. Is that okay? Is there is anybody stuck anywhere in here not seeing what's going on? I can redo some of these arguments in different ways.
Is Q like P1 times P2 times until Pn, then plus 1?
Correct. I multiply all the primes together, and I add 1 to that.
Okay.
Yeah, so let's just suppose, just to illustrate, suppose suppose the biggest prime is 13, right? So suppose we have, these are the primes, 2, 3, 5, 7, 11, and 13. Let's say this is P1 to P6. Then Q would be 2 times 3 times 5 times 7 times 11 times 13 plus 1, right? So this number is clearly bigger than 2, 3, 5, 7, 11, 13, right? It's at least 1 times any of these numbers plus 1, so it's bigger than all of them. And the same argument, if you look at it, you see that none of these numbers can divide Q because it's a, let's say 2. This clearly, this number is odd, right? It's 2 times something plus 1, so it's odd. It's not divisible by 2. Is it divisible by 3? No, because it's 3 times something plus 1. So the remainder when you divide by 3 is 1. The remainder when you divide by 5 is 1. The remainder when you divide by any of these numbers in that list is 1 always, right? So remainder of division of Q by any of 2, 3, 5, 7, 11, 13 is 1. Okay, just to illustrate. Does that make sense?
Yes.
All right. Okay. Notice that this is a non-constructive proof. We don't provide, so when I said that you don't need to do it by contradiction, basically what we're doing here is we're providing we know that this number Q must have a prime divisor not in the list, but we don't say what it is, right? So we're not constructing a new prime from that previous list. In fact, constructing primes is not easy. This is not an obvious thing to do. There are some tricks. So when you read in the paper, oh, they found the biggest prime, what they mean is it's the biggest known prime. There are some recipes. There are sequences of numbers which are believed to produce a lot of prime numbers, but you still have to check that they're prime. But these are really big, so it takes quite a bit of computing power to verify that they're prime. There's a lot of things which are not well known about primes. Here's a couple of things. Here's a little aside, just for fun. I've told you about Goldbach conjecture, right? Is every even number bigger than 4 the sum of 2 primes? This is still not known, right? This is difficult, obviously. We've seen that before. The twin prime conjecture. There's been a bit of progress in the last few years on this, but so what's the twin prime conjecture? We'll say that 2 primes are twin if they are as consecutive as possible. So if there's a difference of 2, right? So so twin primes, that's P and P plus 2 are both prime, right? So for example, 3 and 5, 5 and 7, 11, 13, 29, 31, and so on. Question: are there infinitely many pairs of twin primes? Nobody knows. This is a difficult problem also, obviously. There's been some progress in that area in the last few years, some very, very deep results. in that direction, but not close to actually proving this. This has been around for quite a while. I don't know when it was first conjectured. It's been around for a while. Primes are very mysterious. They're really important and they're very mysterious. I mean, we could spend like hours on this, but we have other stuff to do, I'm afraid. So let's move on to GCDs and LCMs and such. Okay, so all right, you've seen, I'm sure you've seen the notion of greatest common divisor in high school, and you would probably have computed some of them using prime factorization, and that's really nice for small numbers. For big numbers, it's not the right way to do it. It's just too long. So we're going to see a very efficient algorithm to do that, and it not only computes GCDs but a lot more and important and interesting things. But before I present the algorithm, let me define the notion of GCD, and I'm going to go back to the prime factorization theorem and try to see what we can exploit from that and with the GCD to compute the GCD, for instance. Okay, so here's our definition. So I have two integers, a and b, let's say positive, and such that a times b is not 0. So what does that mean? Neither of them is 0, right? That's the same as saying that neither of them is 0. So the greatest common divisor of a and b is denoted GCD of AB. Now I'm not really defining it, right? But it's the greatest common divisor, so it is the largest integer d such that d divides a, d divides a, and d divides b. Okay. Does that always exist? Yes. So you have to be careful. This is a classic where you define something and you think, yeah, okay, nice definition. You play. There's a legend of a PhD thesis. At the start, there's a mathematical object which is defined. This type of structure, mathematical structure, and there's like 200 pages on it, and it turns out that the definition didn't define anything. There was nothing that would satisfy the conditions of the definition. So basically it was 200 pages about nothing. It's for sure it's a legend. This never happened, and if it did happen, the PhD supervisor didn't do a very good job. So here we should make sure that this actually exists, okay? But it does, right? So if you take any two positive integers, one divides both always, right? And so this exists. So there is such a thing because one divides A and one divides B, right? So there is at least one common divisor, and they can't be bigger than A or B, right? And the set of divisors of A and B is finite. So there's a maximum element, there's a biggest one. And so there exists a biggest one. Okay, so this exists. Okay, So here's some examples. Greatest common divisor of 12 and 8. I mean, these are silly, right? But so what's the biggest common divisor of 12 and 8? That would be 4, right? 4 divides both, and you can't find anything bigger. If you divide 8 bigger than 4, that has to be 8, but 8 doesn't divide 12, so that's it. GCD of 17 and 22. Well, 17 is prime, so its only divisors are 1 and 17 doesn't divide 22, so that's got to be 1, right? So that's something that can happen, and in fact, it's important enough to get its own name. So here's a extra definition. So A and B are, we say that they're relatively prime or coprime, relatively prime or coprime. If their GCD is 1. Okay, so they have no common divisor, which is not trivial. So 1 always divides any two numbers, but we'll say that A and B are coprime or relatively prime if there's nothing else. Okay, so list 17 and 22. This is an important and useful concept. We can say a lot of things when relatively prime numbers are involved. We'll see that very soon. Okay, so now let's say we want to compute such a thing. Well, one way which we're going to see would be to use the prime factorization. Okay, this works well unless the numbers get pretty big. Okay, so this is not efficient when A and B are big. Okay, so the efficient way to do this is Euclidean algorithm, which I'm going to show you today, which is a really cool algorithm, and it's very fast. Okay, we're going to see that, but there are things to be done. If you happen to know the prime factorization, you can find the GCD in a very smart and nice way. Okay, so we're going to start with that. So I wish there was, or I should say maybe, I wish I knew how to go back to normal Zoom. But anyway, okay, so let's see what happens if we, so this said, so if we do know the prime factorization of A and B, then computing the GCD is easy. So this is what I want to talk about now. Okay, so I want to do some preliminary work. So some preliminaries before I tell you how to do this. But I mean, again, you may have done this before. Preliminaries. Okay, so you may have done this before. But in any case, just to play around with these concepts, it's good to get our hands dirty. So let's do this. So let's say we have some integer n, positive integer n, and I'm going to write out its prime factorization. So what does that mean? It means that I'm going to write n as a product of primes. Now, some of these primes might appear several times, so I'm just going to put a power. So let's say this is P1 to the A1, P2 to the A2, right up to Pk to the AK, where the PIs are prime and the exponents are all at least 1, okay? You don't want to put a 0 there, then you don't need to put the prime, okay? I will tweak that in just a sec. But this, so this, by the fundamental theorem of arithmetic, is unique. This is the only way to do this, okay? So by the fundamental theorem of arithmetic, this representation is unique. It exists and it is unique. Okay. So now what I'd like to do is to look at the divisors of n in terms of this representation. So we look at the divisors of n in terms of this decomposition. Representation, decomposition. I'm using these two terms for the same thing. Okay. Okay, so here's our first fact. Suppose that I have a prime Q and it divides n. Then what can I say about this prime? It's got to be either P1 or P2 right up to Pk. It's got to be one of those, okay? So then Q must be in this set. If this is obvious to you, this is wonderful, or maybe not. But at least you know what I'm talking about. So let's just make sure that we see that why this is true. So let's see, because, okay. So if Q divides n, okay, what does it mean? So Q divides n means that I can write n equals Q times m for some other integer. Yeah, I repeat once again, don't use fractions. Just don't write. So Q divides n does just, if you write n divided by Q as an integer, you're just going to just don't do that. I assure you that it's not a good way to think or to go about these things. Just stay on the same line. Just don't divide. Okay. So n is equal to Q times m. Okay. And now if I factor out m as a product of primes, so if we factor m as a product of primes, we get a decomposition of n, right, where Q appears. Does everybody see this? Do you see what I'm talking about? Everybody's watching YouTube. No. Do you do you see what I'm talking about? Or is this just
Like, yeah, I guess is that like from the fundamental theorem of arithmetic? Or?
sorry?
Oh, it sounds like kind of a circular.
Circular? Okay, wait.
I don't know. It just feels like a weird argument. Like I believe fact one. Like I'm pretty sure.
Okay, so you agree that if Q divides n, then n is equal to Q times some integer, right? So now factor, so by the fundamental theorem of arithmetic, m can be factored as a product of primes. I don't want to write it out because it's going to get just too heavy. So now I've got n equals Q times a bunch of primes. So far, so good? So now n is represented as a product of primes, and q appears in that decomposition.
Okay.
By uniqueness, since if you look up at the top of the page, that's the representation. There is only one. Q has to be one of those primes. Maybe, maybe not. Yes. I don't know how to explain this differently. Honestly, I've thought about it because I know there might be something which is like not. It's just like you go to. I see what when you're saying it looks circular. I know what you're saying. It's not, but somehow I see what you're saying. But I just really want to avoid writing M as a product of primes. We could, but then I just introduce a whole bunch of new letters for other primes, and I don't want to do that. Just try to see that if Q divides N and Q is a prime, then Q must appear in some decomposition of N as a product of primes, right? But if it does, it must be one of those primes that I started out with because that representation is unique. Let me try to, I don't know if this is going to help, but let's just take a number, 120. Let me factor that. So 120 is 12 times 10, which is 2 times 2 times 3 times 2 times 5, which is 2 cubed times 3 times 5. Okay, is that right? Yeah, okay. So now think of a prime that divides 120. So let's say Q divides 120, and Q is a prime. So 120 will be equal to Q times other primes, right? I can factor everything out into primes. But this must be the same as that. There's no other choice. Because the fundamental theorem tells you it's unique. So Q can't be 17 because it's not in that list there. It must be 2, 3, or 5. Yes?
I think that makes sense. Yeah.
All right, good. Okay, so let me go back to the fact that I stated. So any prime that divides n, if n is written like this, the only primes that divide n are those guys that appear in that factorization, which is unique. It is the only way to factor out n. So 120, the only primes that divide 120 are 2, 3, and 5. That's it. Okay, so that's okay. So now our second fact, which is based on the first fact. So again, I just want to copy this. Copy. Paste. Okay. Let's put this here. Let's take this here like that. Okay. Now, what I want to do is use this trick to describe the divisors of n. Okay. So so let M divide N. M is any positive divisor of N, okay? So now think of it this way. I'm going to factor M as a product of primes. Each of these primes has to divide N. By the first fact, it means these primes have to be P1, P2, right up to Pk, nothing else. So any prime that divides M must be among those primes. So if I look at the unique factorization of M as a product of primes, the primes that are used have to be some primes in P1 to Pk. Sorry. Okay, so that's what I'm going to write. Okay, then M is equal to P1 to the B1, P2 to the B2, Pk to the Bk, where? Now, this looks like the unique factorization, but it's not. Okay, so I had to sort of, it's not a cheat, but I to make things simpler, I'm allowing here. So is every of these primes actually appearing there? No, not necessarily. I can remove some primes. So I'm going to allow the exponents to be 0, okay? But they can't be bigger than the exponent in n. Okay, so sorry, let me just change that. So each bi is between 0 and ai. Okay, before I show you why this is true and try to explain, let me just use my example of above. Whatever. Okay, so we've got 120, which is 2 cubed times 3 times 5. Is that it? Yes. Okay. So the divisors of 120, I'm claiming, have to be, so divisors of 120 are all of the form 2 to the power something times 3 to the power something times 5 to the power something. B1 can be any number between 0 and 3. B2 is either 0 or 1. And same for B3. Okay, you can actually list them all, right? So there's, you just, for instance, there's, well, if you take all zeros as exponents, this is 1. You can take a 1 here. That will be 2. Keep on going, right? So there's a whole bunch of them. Does that make sense? Am I making sense, or is this just like totally? Yeah.
Yeah, that
Makes
yeah,
sense to
it's
me.
sense.
Okay, excellent. Okay, all right. So if you want to list all the divisors of 120, you just look at, you take 2, 3, and 5, and you look at the powers. For 2, you can put any power, but it's 0, 1, 2, 3, and you'll take a 3 or not. Power 0, 1, and 5, you'll take it or not. So there's 15, there's 6, there's 12, there's 10. All these, you can just list them all this way. You can actually count them very simply also in this, but that's another story. Okay, so let's just, okay, let me just briefly just explain. Okay, so this is my example to illustrate this. It's not a proof, obviously, but let's just, I don't want to spend too much time on this, but proof of fact 2. Okay, so by fact 1, any prime q that divides M and will divide n also is in P1 to Pk. Okay, so if Q divides M, M divides N, then Q divides N, first fact says it must be one of those primes. So certainly M must be a product of these primes if there's no other choice. So it must be of this form. Okay. All right. So why are the exponents no less than the AI? Hopefully that's intuitively clear. And finally, Pi to the Bi divides M implies Pi to the Bi divides N. Okay, where am I going with this? Well, it means that N can be written as Pi to the Bi times other primes. I mean, maybe Pi might appear, but a bunch of primes, right? So I get, again, a factorization of N as a product of primes. There is only one way to do that. So for sure, the Bi there can't be bigger than AI. It could be smaller because in that bunch of other primes, maybe Pi appears again. So by uniqueness, Bi has to be at most AI. Okay. I mean, again, when you're not sure, just, you know, think of the example 120, try to see, well, is it possible that you know, if you go back to 120, could you have 2 power 5 appear in the factorization of a divisor? No, because otherwise 120 could be written as 2 power 5 times something else, but that's not possible. 2 appears exactly 3 times. It's like orbits in molecules, atoms, whatever, right? So 2 appears 3 times, and that's it. It can't appear 5 times, can't appear twice, only twice. It's exactly 3 times. Okay. All right. So what was the point of this? Well, I've done the hard work. Now I can show you then so here's our first theorem then, which is now easy. I've done all the hard work. If an integer a is almost okay. So sorry, let me just okay. So I'm going to do one little thing here. I want to express the GCD of two numbers AB in terms of their prime decomposition, Okay. Now, if I'm really being super formal, I would write the decomposition of A, I would write the decomposition of B, and I don't know which primes are which, but there's only finitely many primes that are going to be used total. And so to make the notation much simpler, what we do is the following trick. We just say, okay, list all the primes that appear either in A or B and express their prime decomposition in terms of all these primes. So I'm allowing some exponents to be 0, which so it's not the actual exact prime decomposition of A and B I'm using, but a slight tweak, okay? For ease of notation, right, like this. So A will be P1 Oh yeah, I used AI and okay, so C1, P2 to the C2, right up to PK to the CK. And B, and I'm going to use the same primes. That's the trick, okay? So I'm going to use the same, exact same primes here. I'm going to show you an example. You'll see what I mean. So like this, where the CI and DI are allowed to be 0. Okay, so let me just put a remark here. So we allow exponents to be 0 to have the same primes appear for A and B. Okay, and you'll see why I do that in just a sec. But here's a to illustrate what I'm saying here. Let's say that I look at the numbers. I had an example here which was smart, I think. Okay, so let's say that I look, okay, 120. We saw that earlier, right? So this is 2 power 3 times 3 times 5. Okay, but let's say now that I also consider 500. I'm basically what I want is to compute the GCD of these two numbers. So 500 is 2 squared times 5 cubed. Okay, now you see that the primes that appear in both are not the same. So 3 doesn't appear as a prime in the decomposition of 500. Okay, but what I'm going to do is I'm going to fake it. I'm just going to add it in, but put an exponent 0 so that it's the same numbers that appear. I can always do that. There's only finitely many primes appearing in total. Okay, so that's what I mean by, so you see, you can always expand both decompositions to allow, so you allow exponent 0 so that the primes that appear in both are exactly the same. Okay, why do we not do that in general? Because then the decomposition is not unique. That's the thing, right? So the decomposition which is unique, the exponents have to be at least 1, obviously, because otherwise you can just, that's why 1 is not a prime. It's not a good thing to have 1 as a prime, okay? So I want to compute the GCD of these two guys. Well, might as well continue the example, right? So what is the GCD of 120? I'm curious, by the way, did they make you do this in high school at some point? That kind of stuff?
Not that I remember.
No? Okay.
They talked about GCDs, but they didn't do anything like this.
Yeah, yeah. Sounds familiar. Okay, so GCD of 120 and 500. So I'm looking for a divisor of these two numbers, which is as big as possible. Okay, now take a look at this. That's the key. So we've seen earlier that the divisors of a number, what you do is you look at those primes that appear in the decomposition, and you look at powers which are at most the power and the decomposition. So you can see exactly what the divisors, the common divisors of these two numbers are. You're going to take 2 to a certain power. You're going to take 3 to a certain power and 5 to a certain power. Now, if it's going to be a divisor, that power has to be at most, well, if I take 2, the power is at most 2, because otherwise I'm not going to divide 500. So this is at most 2, right? For 3, well, it has to be at most 0, because otherwise I'm not going to divide 500. And for 5, it'll be at most 1, because otherwise I'm not going to divide 120. Right? Okay. So what did I do? I looked at the smallest of the two exponents and I said it can't be bigger than that. Now I want the biggest divisor of both. So what you do, you take that value, that maximum value. So the greatest 2 to the 2 times 3 to the 0 times 5 to the 1. Take the minimum of the exponents, right? So that's how I managed to find the greatest common divisor. Okay, so you look at the decomposition, I use the same primes. Look at the exponents, then the smallest one, I can't do better than that, but that'll work. I use for each prime, I use the minimum exponent, the minimum of the two exponents that I see, multiply all that together, that'll give me the GCD. Okay, so now what I'm going to do is to state that. So I'm going to copy this. What are you doing? This is what I want. Okay. All right, so I've written my two numbers like this. Oh, let's not do that. Okay, theorem. Let A and B be like this. Then, or the PIs are primes, right? So then the GCD of AB is, and this is exactly what I've shown you. You take P1, the exponent will be the minimum of C1 and D1. So P1 to the, let's call it M1, P2 to the M2, right up to PK to the MK, where MI is the minimum exponents there for all I. That's the GCD. Okay, hopefully this makes some sort of sense, but if it's sort of not clear right now, what you do is you do a bunch of examples and you'll see, I mean, this is not super deep, right? I mean, what's deep is the fundamental theorem of arithmetic in a sense, but because of the fundamental theorem, this comes out of it, okay? So if you're computing GCDs and you happen to know the prime decompositions, it's easy. It's just, right, you take the minimum exponent, okay? So that's how it works. But that's, again, this is assuming you know the decomposition, right? Finding decompositions for big numbers is not efficient. That's not the right way to do it, okay? Does anybody need me to explain this more? Or is the example sort of clear enough to illustrate why this is true? I can spend a bit more time on this if necessary, but if not, I'll just move on because I have like other stuff that I want to do.
I don't know about the others, but I'm good.
All right, thank you. So let's go now to the least common multiple, and then we'll connect both. Okay, so the least common multiple of two integers a and b, positive, okay, is denoted LCM of AB. It is the smallest integer m such that A divides m and b divides. So this is in the other direction, right? So we started by taking two integers and looking at something below them, which divides both, which is the biggest. Now we're looking at the other side. We're looking at all the multiples of a and b. They're common multiples. So numbers that both a and b divide, and we're looking for the smallest one. And there is such a thing, right? So is there a common multiple of a and b? Yes, a times b is always a common multiple, right? So ab is a common multiple. It might not be the smallest, right? So here's an example, right? Just let me just write it down right now. So LCM of 8 and 12. What's the least common multiple of 8 and 12? It's not 8 times 12. That is just too big, right? So 24 is good. You can't do better than that. So it's twice 12 and it's 3 times 8, right? And you can't do any bigger than that, smaller than that, because smaller multiple of 12 would be 12, and that's not a multiple of 8. So that's it, right? So again, let me go back to my fact. So it exists, AB is a common multiple, and so by induction, yeah, by the principle of induction, I'll just leave it like that. But I mean, obviously, yes, there exists a smallest. Principle of induction is just another way of saying that every non-empty subset of the natural numbers has a smallest element, which is, it seems, because we've been raised with the natural numbers, this seems like a totally obvious observation, which in a sense it is, but it's still an axiom. But anyway, so there is a smallest common multiple of any two positive integers, okay? Now, how can we find, I've done all the hard work. Okay, so theorem. I'm going to simply go to the, I'm going to cheat here. I'm just going to copy this. It's not cheating. Yeah. I just can't do it on a blackboard. Let's do that. Okay, so I'm gonna tweak this. Okay, so I want a formula to compute the LCM. Okay. So let's do this. Let's call these big M1, big M2, big MK, big MI. Okay, so I have my two numbers A and B, and I want a number that both A and B divide. So by the earlier work, if these AB divide this bigger number, I know that these primes P1 to PK will all have to appear in the decomposition of the big number, but I want that big number to be as small as possible. So I'd be really silly to add anything other than P1 to PK. Adding a new prime is not going to make it small. So I can just forget about those. So I'm just going to be using P1 to PK. Now I want A and B to divide this number, so the exponents have to be, Ci and Di have to be at, C1 and D1 have to be at most M1. It has to be bigger than both of those. And to make it as small as possible, I'll just take the maximum. Okay, so that's the trick. Okay, so that's the change here. I should maybe write it in, you know what, here's what I'm gonna do. Here we go. Isn't that cool? Okay, so let's take an example to illustrate this. Okay, so same example. 120 we had is 2 cubed times 3 power 1 times 5 power 1. 500 is 2 squared times 3 power 0 times 5 cubed. Okay, I want the LCM of 120 and 500. So I want a number that these two numbers divide, and I want to make it as small as possible. So I'm not going to use the prime 7 or 13 or anything else. I don't, it would make it too big, right? So I just want to use 2, 3, and 5. And if 120 is going to divide it, then 2 had better be at the power at least 3. Otherwise, it's not going to work. 120 is not going to be a divisor. I need at least 2 power 3. I need at least 3 power 1 because of the one here, right? And I'll need at least 3 because of the 3 here. I need those, okay? And I don't need to go bigger. That's all I need. So that's it. So it's the maximum power. So GCD, take the minimum exponent. LCM, take the maximum exponent. So again, if you have the decompositions, computing this is easy as computing max and min of exponents. That's it. Okay. Now, there's a consequence of this, which is pretty cool and is not so obvious to see if you don't have these formulas. So here's a nice consequence of these results. Again, I'm not saying, but if you have questions, please do not hesitate. So I think in the book, this is theorem, I don't know why I remember this, it's theorem 5. Yes, okay. So this is actually a pretty cool little observation. So if you take any positive integers and you multiply the GCD and the LCM, so you'll ask, why would one want to do such a silly thing? Well, because the result is really cool. It's A times B. So the picture I have in my mind is the following, because I know other stuff. So this is sort of a classic identity in a bunch of algebraic structures that you've never seen before, which are called lattices. And the integers happen to be a lattice under divisibility, and it looks like a something like that. Okay, so the way I see it is this: you have A like that, you have B like that. A and B, they divide, both of them divide the LCM, and both of them are divided by the GCD. So I sort of see it like that. And what it says is that if you multiply both ends of this square, you get the same thing, right? So you multiply top and bottom, or you multiply left and right, and you will get the same thing. Let's just erase that. Okay. I mean, that's sort of irrelevant here, just a picture. Okay, so why is this true? So why? So use previous two formulas and observe. Okay, so I'm multiplying LCM of AB by GCD of AB. Okay, I'm going to use the same notation that I had. So left-hand side is P1 to the big M1. Oh, I'm happy I used that. Good. PK to the big MK times P1 to the little M1, P2 little M2, PK to the little MK. This is just the left-hand side, but when I multiply this, what do I get? Of course, I can put those primes together in the obvious way. So this is P1 to the big M1 plus little m1, P2 to the big M2 plus little m2, and so on right up to PK to the little big MK plus little mk. But now, this is a cool observation. If I give you two numbers and I say, take the minimum of these two numbers, then take the maximum of these two numbers and add those together, what do you get? It's the sum of the two numbers, right? So 2 and 3, the minimum is 2, maximum is 3. The min plus the max is 2 plus 3, right? And if they're equal, it makes no difference, right? So this is just the original number, right? So it's P, I mean, it's the exponents of the sum of C1 plus D1, C2 plus D2, PK, CK plus DK. This is A times B. Since max of XY plus min of XY is equal to X plus Y. Does everybody believe me?
Yeah.
Yes. Okay, so that's it. That's where it comes from. That's all. So the GCD times the LCM is equal to A times B. Proving this without the prime decomposition is, actually, I haven't thought about that in a while. Is that, yeah, I don't know. I'd have to think about it. But without using the prime decomposition, I'm not sure. I have to think about it. But that's easy. Once you have that, it's easy. Okay, this is not going very fast, is it? Okay, let me, I'm always saying let me like you had a choice. So let me, please. Okay, Euclidean algorithm. So again, what I've done up to now, if you do have the decomposition available, then you can do these things. If you don't have the decomposition, what you don't want to do if you have fairly big numbers is to find the decomposition. That is not efficient, or at least nobody knows an efficient way of doing it. If you do find an efficient way of doing it, let me know. Okay, so I'm going to show you the Euclidean algorithm, and please keep in mind that it's good for that, but it's good for tons of other stuff. So this is a very efficient, very fast algorithm, very efficient algorithm to compute the GCD and also used to compute many other things. I mean, it's remarkable. It's just so darned clever. I mean, it's been around for dozens of centuries, and it's still like, I mean, it's so cool. And it's like super simple. It's based on the following observation. I mean, there was a time, I have to say, that a long time ago, Euclidean algorithm was sort of, yeah, there's something I didn't quite get. But for me, like the key thing I'm going to give you here, the key thing, if you remember that, you will always understand the Euclidean algorithm perfectly and never forget it. You'll know exactly how it works just by this. This is the key fact. Okay, so this is the key observation. I mean, the whole thing is there, and it's an easy observation. Okay, so the whole algorithm is built on the following observation. Okay, so I'm going to write this as a lemma. Okay, so let A and B be integers. Do I need, no, I need nothing else. And write A equals BQ plus R using the division algorithm, right? Okay, in other words, the key point is, actually, you don't even, no, you know what? Just let's make it even, just forget that. You don't even need that, okay? Then, okay, so let's say we have AB in Z plus. I'm writing it this way because I am going to use the division algorithm, but I don't need the division algorithm here at all. I just need to write A as BQ plus R, okay? Q and R are just integers, doesn't matter, okay? Let D be some positive integer. Then, so here's a claim. So I'm making this more complicated than it should be, but okay. So what I'm saying, what I want to say is this, then D divides A and B if and only if D divides B and R. All you have to understand is this, okay? And I'm going to show you why this is true. It's one line, okay? But that's the whole Euclidean algorithm is based on this fact, okay? I've lost people. I don't like losing people. Makes me feel inadequate. Okay, so why is this true? Okay, proof. Maybe, okay, a good, I don't know how this works through a screen, but anyway, a good way to approach a course like this is if you can reach the level where you're asking yourself, okay, why is this true? So you're looking at the lemma that I just wrote and you're thinking, okay, why would this be true? Not even just, you don't have to figure it out, but just if your natural instinct is to ask yourself, okay, why is this true? You're on the right track. It, even if you don't answer your question, makes no difference. But if you have that impulse to, why would that be true? Right? This is really good. So why is this true? Well, so let's do this direction, right? So D divides A and B implies that D divides A minus QB right? If you divide two numbers, you divide any combination of those. And what is A minus QB? It is R. So if D divides A and B, it divides B and R. Okay. For the other direction is even easier. And if you've understood what I just did right there, you can probably do it by yourself, right? So now suppose D divides B and R. What is A? It's B times Q plus R. So D must divide A also. So D divides BQ plus R, which is A. So D divides, because it divided B already as a hypothesis, and B. Okay, so if A is equal to BQ plus R, then the common divisors of A and B are the same as the common divisors of B and R. They are the same. So they have the same GCD. Now, when you're using the division algorithm, that remainder gets small. So you repeat and you're going to find what you want fast. Okay, so let me show you. Okay, I don't know how, I mean, so I have a PhD student at this moment, and of course we're working through Zoom. And so when he's showing me stuff that he's been doing, he zooms a lot like this, and going like this and like that, and I just go nuts. I have like this huge screen, and I just go nuts when he does that. So I don't know how this is good for you or not, because I didn't used to do that before. But okay, let's. So here is an example of how to use this. Okay, so I'm going to find the GCD of 91 and 287. Okay, so my observation says that if I use the division algorithm, so step one, I'm going to write 287. I'm going to divide by 91. I'm going to cheat and just look at my notes. This is 3 times 91 plus 14. Okay. Now, the lemma says that the divisors of these two numbers are exactly the same as the divisors of these two numbers. Right? So they must have the same GCD. They have exactly the same set of common divisors, right? So the common divisors of 287 and 91 are exactly those of 91 and 14 by the last lemma. Okay, so if I'm looking for the GCD of 287 and 91, it's the same as looking for the GCD of 91 and 14. Okay, so the GCD of 91 to 87 is the same, very, very same as this one. So I forget about 287 and work with 14 and 91. They're smaller numbers. I'm happy, right? So what do? Repeat. So I'm going to take 91, use the division algorithm. That's 6 times 14 plus 7. division algorithm, right? What does my lemma say? It says that if you look at the common divisors of 91 and 14, they are exactly the same as those as 14 and 7. And you see we're done, right? Okay, so GCD of 1491 is the same as the GCD of 714. And what's the greatest common divisor of 7 and 14? Of course, it is 7, right? But just to show you what happens if you're a machine and you're not smart, you just follow instructions. What happens if 1 is a machine, not you? I'm not accusing you of being machines. We're all machines, but step 3. So I repeat, right? 7 and 14. So 14 is 2 times 7 plus 0. Of course, we're going to get 0, right? But that's your stop sign, right? It means you're done. So what does the 0 say? It says that the previous pair, one divided the other, the smaller divided. This means, right? So it means 7 divides 14. In other words, GCD is 7. And since at each step I keep the same GCD, the original GCD was 7. So GCD, maybe I'm going too slow, I don't know. I think no, we can never go too slow, I think. But I mean, if I'm boring you, I'm sorry. Read a book. So that's my GCD after these basically 2 steps, right? So that's the trick. That's the idea. I mean, once you once you know this trick that if you use the division algorithm, the GCD of your first 2 numbers is the same as the GCD of the next 2, and you just repeat, and that's it. That's the whole. There's nothing else. There is really nothing else, right? So I could write it as an algorithm and this and that. I might do it next time. I don't know, but basically that's it. Okay, so I'm gonna do another one. Let's do another one. So this is a repeated application of the division algorithm using this lemma that says each time the GCD is the same. That's it. Okay. Okay. Let's find the GCD of 414 and 662. Now, again, these numbers are very small. I mean, if I use, I could factor them out and use the other method. Obviously, the numbers are small. I mean, but that's not really the point. For really big numbers, Euclidean algorithm is used for sure. Any machine will be using the Euclidean algorithm. It's not going to factor. Second, the actual algorithm is going to help us compute more sophisticated things soon, next class, almost. Okay, so I take the biggest of the 2 numbers, 662. I express it as a combination using the division algorithm. So this is 1 times 414 plus a remainder of 248. Okay, division algorithm. I'll start writing it. I'll just write it here, but okay. I repeat now with 414 and 248. This is 1 times 248 plus, I'm cheating, eh? I have the answers right here. If we were doing this live on the board, I'd be actually doing it on the board, but you see what you're missing. Amazing, amazing. Yeah, okay. 248. Why did this, what? Okay, 248. equals 1 times 166 plus a remainder of 82. And then 166, 1 times 82. You see, I'm just repeating until something happens. This is, no, not once, that's twice. The twice 82 plus 2. And then finally, 82 is 41 times 2 plus 0. That's my stop sign. What does it tell me? It says that the previous pair, one divided the other, right? And I know the GCD of all the pairs is always the same. So the GCD, let me just, that's the last example where I'm going to explain the method. After that, I'll just tell you. So this, so the last non-zero remainder is the one you're looking for, right? So this is the GCD we seek. It's the last non-zero remainder. Okay, why is that? Because the GCD of 662,414 is equal to the GCD of 414,248, which is equal to the GCD of 248,166, which is equal to the GCD of 166,82, which is equal to the GCD of 82 and 2, which is 2, right? It'll stop in a pair where the smaller divides bigger one. Now, if you're a very computer scientist-y oriented person, you might be asking yourself, oh, is this correct? Well, yeah, of course it's correct, but what makes it work? The key idea is that lemma, but there's another key idea, which is really important, is that this thing terminates. This algorithm terminates. Why? Because the remainders are getting smaller and smaller and eventually must reach 0. There's no way this is going to get stuck in a loop anywhere. The remainders must get smaller and smaller. Yeah, okay. So next time I will make this a little clearer, but let me add it here. So notice algorithm must terminate because the remainders get smaller and smaller, strictly smaller. Hence, must reach 0. Yeah, I told you I had these papers to read for this conference, and I finished last Friday. I worked all my last week reading papers, 16 hours a day. It was wonderful. And one of those
Hey,
papers.
it's done. It's finally done.
Yes, yes. Sorry, somehow I didn't know what you were talking about. Yes, it's done. One of those papers has like this huge algorithm in it, and unfortunately, it wasn't really an algorithm. It didn't work, but it's really hard to figure out why it doesn't work. But the reason it didn't work is that it didn't terminate. Just for that little baby reason right there. That's if you're writing like this big algorithm, make sure it actually stops, okay? Because it might look real good, and it looked real good, but you know. So yeah, okay, all right. That will be it for today. If you have questions or comments, now's the time. Maybe I'll stop recording. Maybe I'll make you